Today we are going to discuss the second part of chapter 4, which is sound waves. And we already said that the sound is a longitudinal wave, means the particles of the medium vibrate in the same direction of the wave. But how do we hear sounds? And we already said sounds produce condensation and rarefaction zones, so the vibration can move through the air. Then the vibration reaches to the eardrum, and the ear sends a nerve signal to the brain, and the brain interprets the signal as sound. Now, can we hear all the frequencies? Then the answer is no. We can hear some range of frequency. We can hear from 20 Hz to 20,000 Hz. And we can detect just this frequency, the sounds of these frequencies. Below to 20 Hz, we cannot hear that sounds. This corresponds to the infrasound region. And there are some animals that can detect that sound. For example, the elephants can detect sounds in the infrasound region. Also above 20 Hz, also we cannot detect that sounds. This corresponds to the ultrasound region. And for example, there are some animals that can detect that sounds, and in this we had the bat. And the bat can detect ultrasound frequencies. Then also we discussed the sound requires a medium to propagate. Then the medium can be gas, liquid, or solid. Then we can see in this table the sounds travel faster. The speed of the sound is faster in solids than in liquids or gases. And the reason is because in solids, the molecules are closer than in liquids or gases. So the sound waves can propagate efficiently in solids than in liquids or gases. Now we had a table with different velocities, and this I just want you had some reference to understand your answers when you are solving problems and you get some value of velocities, then you will have idea if your answer is correct or not. Then for example, if we had 1 meters per second, then this correspond in miles per hour correspond to 2. And this is just when we are walking. This is the speed when we are walking. But if we say 10 meters per second, this corresponds to about 22 miles per hour. This is the speed in a school zone. If we say 30 meters per second, this corresponds to 67 miles per hour is the maximum speed in the highway. Now, if we say 300 meters per second, this corresponds to 670 miles per hour. This is the speed of the sound in air at room temperature. It's more or less the speed of the sound in air. Then we can see the speed of the sound is 10 times the speed in the maximum speed in the highway. Yes. Now, if we are talking about the speed of the light, this is 300 millions. Yes, 300 millions meters per second. This corresponds to 670 millions miles per hour. And we can see the light travels 1 million faster than the sound. Yes. Then if you are calculating, for example, the speed of the light, yes, and your answer is 300 or 200 or is 0.5 meters per second, then we know something is wrong in the problem. Yes, we know we had the wrong answer. And this is why, because of this, because the light is faster than the sound, then this is why if there is a lightning, first we see the flash of lightning and then we hear the thunder few seconds later. Also, the velocity, the speed of the sound is influenced by the temperature of the earth. Yes. When the sound is traveling in earth, then the velocity of the sound depends of the temperature of the earth. For example, if the temperature of the air is -1 degree Celsius, the speed is 330.4 meters per second. If the temperature is 21 degrees Celsius, the speed is 343.6 meters per second. If it's hot, yes, it's really hot, it's 45 degrees Celsius, then the speed of the sound is 358 meters per second. Then why this happens? When the temperature increases, then the molecules of the air move faster, and this increases the kinetic energy of that molecules. And this is why this increase the speed of the sound, because the molecules of the air are moving faster at higher temperature. But there is a relation of the velocity and the temperature. Then the velocity of the sound increases in 0.6 meters per second for each degree Celsius. And there is that relation, that we can use that relation to calculate the velocity of the sound at any temperature. One more thing we know is at sea level, in dry air at 0 degrees Celsius, the speed of the sound is 331 meters per second. Then what we will do is we will use this information to find the equation that we can use to calculate the velocity of the sound at any temperature. Then now we know for each degree Celsius, the velocity of the sound increases in 0.60 meters per second. Also, we know at 0 degrees Celsius, the speed of the sound is 331.0 meters per second. 331.0 meters per second. Then using this information, we want to find the equation that correlate velocity and temperature. Is we want to find, try to plot and find the equation of this graph. And we have meters per second, and here we have temperature in degrees Celsius. Then we know one point, yes, we know at 0 degrees Celsius, the speed of the sound is 331. Then we know this point, yes, of the graph. We know at 0 degrees Celsius, here is 0, the speed of the sound is 331. Then we know at least one point. Then this corresponds to 331 meters per second. And let's see how we can get the other points. Then we know this relation. The speed of the sound increases in 0.6 each degree Celsius. Then this is a ratio. This is like slope. Then we can use the definition of a slope. let's find and in this case will be the change in velocity over the change in temperature. And in this case we know for each degree Celsius the change in velocity is 0.60 meters per second. And we can generate the other point of the graph. As we remember, this is rise, this is run, and we run 1 unit and we move 0.6, then we will find 1 point here. We run 1, move 0.6. Of course this is not at a scale, okay, this is just, and then we can generate all the points where we move 1 degree Celsius, we run 1 degree Celsius, we rise 0.6, we run 1 degree Celsius, we rise 0.6 meters per second. Then we can see if we can generate all the points we want, and then we can see what we had if we connect the points. We had a straight line. Then the equation that correlates velocity and temperature is a linear relation. Yes, it's a linear relation. And we know how to, let's see if I can graph better this, if I can. Then we know what is the equation for time. Yes, we know linear relation. Then we know the general equation for any line is y equal plus b. Y in our case will be the velocity of the sounds. The slope will be 0.6 over 1. Then we can rewrite this one as in a simple way. Let me write here. In a simple way, we can write this one like 0.60 meters. So we can write in that way. Then the speed will be 0.60 meters per second per degree Celsius. Then x in our case corresponds to the temperature. Plus, what is the y-intercept? Is 331.0. In this case, let's write the units will be meters per second. Then this is the equation we can, let me write this one there. And this is the equation we can apply to calculate the velocity of the sound in air at any temperature. This works only if the medium in which the sound is propagated is air. And we can apply this equation. The same equation is in your textbook. Just in the textbook is appear in this way. First, the y-intercept and then this part. But you can see it's the same equation. And this is how the equation appear in your textbook. And we can see it really is the same linear equation as we had here. And this is the equation is in your textbook. And we can see this is the velocity of the sound. This corresponds to the velocity of the sound at 0 degrees Celsius is the y-intercept, as is 331, and here is the slope, yes, is the slope, and then And here we had the temperature in which we want to calculate the velocity of the sound. For example, if we want to calculate the velocity of the sound at 30 degrees Celsius, then what we had to do is just we apply this equation, then 331 plus 0.6 multiplied by 30. This is the temperature in which we want to calculate the velocity of the sound. And we multiply first these two numbers, and we can see the degrees Celsius cancel out. And we had 331 plus 18, and then we will have 349 meters per second. Then you can see we can apply this equation to calculate the velocity of the sound at any temperature. But one thing is important is the temperature must be in degrees Celsius, because we had the slope, as the units that appear in the slope is in degrees Celsius. The temperature must be in degrees Celsius. And here is again the same equation. And also, if we want to calculate, or if we need to calculate the velocity of the sound in feet per second, then in this case, the velocity of the sound at 0 degrees Celsius means the y-intercept is 1087 feet per second, is this number. And in this case, the slope in feet per second it will be 2. Then in each degree Celsius, the velocity of the sound increases in 2 feet per second. And this is why the slope in this case is 2. If the velocity of the sound is in feet per second. And you can use either this equation or this equation to calculate the velocity of the sound at some particular temperature. But this is the velocity of the sound in Earth. One more thing, the temperature must be in degrees Celsius. And let's try to solve one problem. And we want to know what is the velocity of the sound in meters per second. Then we need to apply this equation at room temperature. Room temperature is about 20 degrees Celsius. And we know the temperature is 20 degrees Celsius. Then now just we apply the equation. The velocity equals of the sound equals to 331.0, which is the velocity of the sound at 0 degrees Celsius, plus slope 0.60 meters. And then we multiply by the temperature. Let me write like that, and then we replace the value. And the temperature here is 20 degrees Celsius. And we can see this degrees Celsius cancel out with this degrees Celsius. And now we had meters per second. Then we had meters per second, no problem. We can add these numbers together. Yes. And now we multiply and then we add. Yes. First we multiply, and we multiply these numbers together, and we will get 12.0 meters per second. And we add these numbers together, and then we will have 343 meters per second. And the velocity of the sound at this temperature at 20 degrees Celsius is 343 meters per second. Now let's solve one more problem. Then if the air temperature is 86.0 Fahrenheit, And what is the velocity of the sound in feet per second? And now we have the temperature of the air is 86.0 Fahrenheit. And what happened is this, in order to have consistent units, we need the temperature in degrees Celsius. Then this is why if the temperature is in another unit, for example Fahrenheit, we need to convert this temperature into degrees Celsius. And in this case, we need to apply this equation to convert Fahrenheit into degrees Celsius. In the step number 1, we convert the temperature in degrees Celsius. And we had here 86.0 minus 32, and then we will have 54. And here you can solve, it's all up to you. You can multiply 54 by 5 and then divide by 9. Or just you can divide 54 divided by 9 will be 6, and 6 times 5 is 30. Then it's up to you how you want to solve this problem. And let me here do something. And write the correct number. 0.0. Then we will have here 30.0 degrees Celsius. And 86 correspond to 30.0 degrees Celsius. Then now we had the temperature in degrees Celsius. Then what we need to do now is to calculate the velocity of the sound. Yes. And because in the problem they ask to give the velocity in feet per second, then we need to apply this equation in this case. And let's write the equation here. Then we know the velocity of the sound at 0 degrees Celsius. Remember, this is the y-intercept, correspond to feet per second plus slope, in this case is 2 feet per second, and then the temperature in this case will be 30 degrees Celsius. And now just we need to solve. The velocity will be feet per second, and we can see here again this cancel out, and we had feet per second. This is the units we want. And here we had 60.0 feet per second, 2 times 30, 60, and then we add, yes, then no decimal places in the answer because we are adding, then we will have 1,147 feet per second. And this is the velocity of the sound in air if the temperature of the air is 86 Fahrenheit. And this is all I had to discuss in this presentation.